Hello and welcome to Chemistry Topic by Topic Live. We're going to have a look today at trying to play around with some more nasty equations and sorting bits and pieces out. We're going to try and look at masses in reactions, and we're going to have a look at yield, and we're going to have a look at atom economy, and then trying to make a solution up, because unfortunately I've run out of solution and I need some more. So let's start having a look at masses and balanced equations. So let's get going, have a look at this. Right, okay, so what I've got is some sort of thing to work out. Let's revise some things first. Let's choose a substance. I've got sodium sulfate. Now when I look at something like sodium sulfate, we know that sulfate, this is 2 minus. We know that sodium is 1 plus. So to get these to work, sodium's in group 1, so it's 1 plus. So I will need 2 sodiums to react with the sulfate. So my formula is going to be Na2SO4. We know that sodium has a mass of 23, looking at our periodic table. We know that sulfur is 32, looking at our periodic table, and we know that oxygen is 16. We can therefore use this to try to do various calculations, working out. Let's start with the formula mass. So our formula mass is going to be 2 23s, which is going to give me 46, plus 32, plus 4 16s, which are going to be 64, and I can just use my calculator here to add these up. So that's going to be 46 plus 32 plus 64, which is going to give me 142. So we can easily work out what we've got here. Now let's suppose we do an experiment, and let's look at how we can work out some masses to balanced equations. Let's imagine that I took 13.8 grams of sodium and I reacted that with 9.6 grams of sulfur plus 19.2 grams of oxygen. Now, to work out how much of these react with each one, let's see if we can work out how many moles of each of these we've got. Remember, the number of moles equals the mass divided by the relative here atomic mass. N equals M over MR. And as usual, I've managed to break my pencil. Right, do this first one. Let's work out. We've got 13.8 grams of sodium over the mass of sodium, which is 23. Let's get the calculator out and we'll do this. So it's going to be 13.8 over 23, which is going to give me 3/5 or 0.6. So I've got 0.6 moles of that. Let's work it out for the sulfur. The sulfur then is going to be 9.6 over 32. Put into the calculator. We've got 9.6 over 32, which is going to give me 3/10 or 0.3. I can see someone has done some work on this to make sure this is going to work out nicely for me. And then we've got 19.2 for oxygen, so let's just do these. 19.2 divided by 16, and this is 1.2. So we've got some figures here. We've got 0.6 of sodium reacting with 0.3 of sulfur with 1.2 of oxygen. Let's divide them by the smallest. So 0.3 into 0.3, I can do that without a calculator. That's going to give me 1. 0.3 into 0.6 will go twice, and 0.3 into 1.2 is going to give me 4. These may not exactly work, and in which case you want to get the nearest whole number. So we've got 2 sodiums, 1 sulfur, and we have 4 oxygens. And there we are, Na2SO4. Not surprising really. I worked it out beforehand. Right, so let's now look at a different type of problem. Let's look at an equation, and the equation we're going to have is going to be an acid plus a carbonate. So here we go, an acid, let's choose hydrochloric acid here, plus a carbonate, let's go for potassium carbonate, and that will give me acid plus carbonate gives me a salt, potassium chloride, plus water, plus carbon dioxide. Let's look up some of these numbers in our periodic table. So if I put my periodic table down here, potassium is going to give me 39. Hydrogen is going to give me 1. Chlorine is going to give me 35.5. Carbon is going to give me 12, and finally oxygen is going to give me 16. That's my periodic table used up. Let's see what we can work out. So my HCl is going to be 35.5 plus 1, that's going to give me 36.5. My potassium carbonate, KCO3, is going to give me 39 plus 12 plus 3 lots of 16. 39 plus 12 plus 48 is going to give me 99. This will react to give me KCl. 39 plus 35.5, that's going to give me 74.5 plus water, which is going to be 16 plus 2, which is going to give me here a simple answer of 18, plus we've got CO2, which is going to give me a simple answer of 44. Now, what I haven't done is I haven't balanced the equation. So here is my equation. I've worked out the numbers, but we need to work out how many masses of these are going to react. So let's start by balancing the equation. And I'm going to do that using my can't be asked, CBA. My chemical, the before and the after amount. The chemicals, I've got H, Cl, K, C and O. Hydrogen, before I've got 1, chlorine I've got 1, potassium I've got 1, carbon I've got 1, and carbonate, the oxygen, I've got 3. After, we've got 1 for K, 1 for Cl, 2 for hydrogen, we've got then 3 for the oxygen and 1 for the carbon. So this is the one that's obviously wrong. So if I've got 2 at the end, I must have 2 before. So this is going to give me 2 Cls. 2 Cls means that I've got 2 there. So this is going to have to give me here 2 there. If I get 2 here, then my potassium, I'm going to have 2 of those. If I'm going to have 2 of those, then I've got to have 2 carbons and 6 oxygens. If I've got my Cl here with 2, then I am going to have my 2 Ks. So that appears to be balanced at the moment. My carbons, I've got 2. So if I've now got 2 of these, then I've got 2 2s are 4, and my oxygen here makes 5. We're still not balanced. So we're going to have to work on this a little bit harder. What I need is an extra one here. So let's see what we can do with this. So to try and balance this, we've got to now work a little bit harder. It didn't balance on the first go through. What can we do? Well, we can try some ideas. it appears that it's this oxygen that's causing the problem. That I've got 3 here and I've got 3 here. But the hydrogen, I've got 2, I've got 1 here and I've got 2 there. Doubling the hydrogen, unfortunately, also doubles the chlorine. Doubling the chlorine is doubling the number of Ks I need. And as I do that, so I am increasing the number of carbonates that I'm using. So what looks like a fairly straightforward reaction needs a little bit more work. Let's see what would happen if we try this with 3. If I had 3 hydrogens here, then that's not going to give me an even number. If I start off with 4 of these, then we're going to have 4 here, and if we have 2 there, then we'd also have 4. The chlorines will have to increase to 4. At the beginning, 4 at the end, which gives me 4 potassiums here, which is going to then give me 4 carbons, and on this side 12. Can I get 12 to work properly on this side? If I've got 4 of those, I've got 4 carbons, 4 2s are 8, and we'll have these 9 and 10. So that's still not going to give us a sufficient number. So it's more difficult than initially it looks, because as we're trying to balance HCl with potassium carbonate, we have a discrepancy coming along with these hydrogens and oxygens, because we've got the 1 here, and as this one's increasing, so we need to try and puzzle this out. So let's see if we can resolve this problem. Hydrochloric acid plus potassium carbonate giving me KCl plus H2O plus CO2. If I just put in 2 here, then this looks like it's going to balance. I've got 2 H's here, 2 H's there, we've got 2 Cl's, we're going to need 2 here, that's not right, and potassium chloride having the formula KCl means that we've got a bit of a problem trying to work out how these go. I've seen a few answers of this on the internet, and some people have tried to get it working using KCl2, but I've made a mistake. Now, where have I made a mistake? Well, this is becoming apparent as we start working this out, and which is why we need to work out all these equations properly, because we've got K2CO3, and if we don't get these formulas right, then everything else goes to pot. So I have some of my students who really struggle getting these things right. And unless we get these things right, then everything else falls apart. Now we can balance this quite easily, because we've got 2 of those and we'll have 2 of those. It all works out remarkably well, and we've worked out our molar masses of this, 36.5. This one we failed on because it's 39 times 2 plus 12 plus 16 times 3 gives me 74.5 plus 18 plus 44. We work out this one, and it gives me 136. 138. If we do a sum here, we can work out that our 138 plus our 36.5 gives me on this side 174.5 grams. And if we work out the other side, we should end up with 74.5 times 2 I just realised I made a mistake on the other side. I'll correct that in a sec. Plus 18 plus 44 gives me 211 on this side, and I didn't do 2 HCl's on that side. So it's 138 plus 36.5 times 2 gives me 211 on this side. And I know I've got a balanced equation. So when things go wrong with these, the masses and balanced equations all sort things out. So we need to check very carefully that you've got the formula right. You need to check very carefully that you've multiplied by the right number. And that gives us masses to balanced equations that we can work out. Now, the next thing we need to worry about is trying to get the yield of a chemical reaction. So when we do an equation, we work out what's going to happen. So let's write here calcium carbonate, and this is going to give me calcium oxide plus CO2. Let's ensure we've got a balanced equation to start with. It is. Now, if we do our equation correctly, then we can add up this. Calcium is 40, carbon is 12, and oxygen is 16. So we've got 40 plus 12 plus 3 16s, which is going to give me 100. 100 grams of this would give me 40 plus 16, which is going to give me 56 grams, plus carbon dioxide, which I've worked out already up the top there, which is 44. And 56 and 44 give me 100. So I know we've got a balanced equation. Now, to work out yield, we might be given some facts, and they may say that basically a company might take in 200 tons of limestone calcium carbonate, and what they get out of here when they do it might be 96 tons of calcium oxide. And what is the percentage yield? We know that if I took in 100, I would get 56. So if I took in 200 tons, I can just change the unit, I should get, doubling this one, double that one, 112. So the theoretical for 200 tons would give me 56 times 2, which gives me 112 tons of the substance. To work out our yield, we're going to put the actual mass over the theoretical mass, and we're going to times it by 100. Let's do that. We've got our actual mass, 96 over 112. We multiply it by 100 to work out what it is as a percentage. Let's bring my calculator down. I'm going to do 96 over 112, and I'm going to multiply that by 100. And that gives me 85.71, we'll round it, 85.7%. What sort of factors normally affect yield? Well, these are relatively straightforward. Usually, in my experience, when we're trying some of these things, it's students. And dropping the substance, or having a substance that does dissolve in water, and you try and clean it, and you dissolve it then in a little bit of water, and you watch your yield go down the drain, is sort of a standard thing. We might find the reaction is reversible. It goes both ways. So if I make one substance, it's also going back. That can affect the yield. Sometimes we get extra reactions happening that we didn't predict. Usually, some of the products are lost due to bad handling, due to things being left in the apparatus. We can't get that last little bit out. Sometimes what we think is pure may not be quite as pure as we want, and sometimes that we get some sort of lack of reaction going, in that perhaps the two substances never did come into contact with one another. All of these things can affect the yield of a reaction. So let's look at the second to last thing I want to look at next, which is atom economy. Now, atom economy is something that's not really that obvious, and basically we want to work out what percentage we've got of something. So let's take a substance, and we're going to take nitrogen, and we're going to take hydrogen, and we're going to react these to form ammonia. And I want to work out the atom economy that we've actually got. Now, this reaction, in fact, isn't that, but is largely this. It's mostly going this way. So if I start off with this stuff and try and make that, basically I'm still making more of this. And sometimes these equations here try and ruin what we're trying to do with working out atom economy. Let's look at the reactants and the products. So my percentage atom economy is going to be the mass of the products over the mass of the reactants. Now, for some things this is going to be relatively easy to work out. Here I've only got one product. But what would happen if we had two? Let's suppose we've got something like lead sulfide. And lead sulfide I'm going to heat up with some oxygen, 3O2, and this is going to give me lead oxide. I'm going to have two of those, so two of those, plus I'm going to make two SO2s. What do we know? I know from my periodic table that lead has a mass of 207. I remember sulfur is 32, and I can remember oxygen is 16. So we're going to work out the percentage atom economy. It's going to be the mass of the products over the reactants, and we're going to times this by 100. So the mass of our products, it's going to be 2 lead oxides, and I'm not interested here in my sulfur. I'm not making that. I'm only interested in the substance I'm making. And I'm making that from 2 lead sulfides plus my 3 oxygens, because these 2 are going to make that substance. I've got 2 times 207 plus 16 over 2 times 207 plus 32 plus 3 lots of oxygen, and it's O2, so that's 16 times 2. Let's work out what we've got. I don't look at the screen enough to see that I haven't pushed it up. So I've got 207 plus 16, 223, and I've got 2 of those. So that's going to give me 446. That's going to be over my lead sulfide, which is going to give me 207 plus 32, which is 239 here, times 2, which is 476. Yeah, 478, I can't read. Plus 16 times 2, which we know is 32, times by here 3, because I've got 3 of them, which gives me 96. And I'm going to times that by 100%. Let's do the sum. 446 divided by 478 plus my 96 times by 100, and that should give me an atom economy of 77.7%. So this stuff here, sulfur dioxide, is just given off in this production. This gas is a serious pollution threat, causes acid rain and causes all types of problems. My final thing I want to have a look at is I'm running out of sodium thiosulfate, and this is a little bit of a problem for me because I need an odd solution. I need a 0.1 molar solution of sodium thiosulfate. Where do we start? Well, I need to know my formula of sodium thiosulfate. And my formula of sodium thiosulfate is going to be Na2 S2O3, and if I look at my thiosulfate, it looks like this, and these are hydrated crystals, so I need to look up the hydrated crystals of sodium thiosulfate, and I believe this is 5H2O. So we need to work out all of this. So my formula for this is going to be, I've got 23 times 2 plus, I've got to have sulfur, which is going to be 32 times 2, plus I've got my oxygen, which is 16 times 3, plus we're going to need my water, which is going to be 18, I can work that one out, times 5. We start off then with the calculator and let's put them all in. So I've got 23 times 2 plus I've got my 32 times 2 plus I've got my 16 times 3 plus I have my 5 times 18, and that should give me 248. If I want to make up a 1 molar solution, the definition of this is a 1 molar solution contains 1 mole of my substance, which is my sodium thiosulfate, dissolved to make up 1 litre. So that's okay, but I don't want a 1 molar solution. I want a 0.1 molar solution. I want 1/10 of it. So if I used this one, I would have used 248 grams of sodium thiosulfate, 1 mole's worth. And if I want to use 1/10 of that, then I need to use 24.8 grams of my sodium thiosulfate. Well, let's go over and see if we can actually try and make this up and see what happens. And I've already got everything I need all set up. I've got a balance, a weighing boat, I've got my chemical, I've got my spatula, I've got my amount for my calculation, and I've got, oh dear, I haven't got the right size volumetric flask. I don't have a litre one, I've only got a 500ml one. So I can only make up half the amount of sodium thiosulfate that I need. So let's make up 500 mils, but I want to make up the same molarity. Let's do the calculation quickly. If I've only got half the amount of stuff, so now I've only got 500 mils instead of 1000 mils, I've got half the amount of substance, so this is going to give me 12.4 grams required of my sodium thiosulfate. So we're ready to start working out what I need. So I'm going to switch on my balance. And I need 12.4 grams of my thiosulfate in here. About 4. We're making our way there. I'm just trying to help out by putting smaller crystals in there. This stuff's not too bad to touch. You couldn't do that with all these substances you're trying to work with. 4-2. Oh, it's going to have to be a small crystal. A bit too much. I think I'm going to go with that. That's 12.47, 4647. I think I'm just going to go with that one. So, what do we want to do now? Well, I'm just going to move the balance out of the way. I don't need that anymore. And this is a volumetric flask. And what I'm going to do is I'm going to pour these crystals in here. And I've got to be trying to be careful that I don't actually drop any. Now some substances you will need to sort of wash these through. And there's my substance ready to be dissolved. I want some distilled water. I have some here already. And what I'm going to do is I'm going to put some in here. But I'm not going to fill it up all the way. So I've only put in about 300 mils, 253 mils. And now I can shake this up quite well to try to get my sodiumthiosulfate to dissolve nicely in here. I've still got quite a few crystals that haven't dissolved. I'm going to give them a bit of a swirl. Still a few that haven't dissolved. Just a few more. I'm going to help it by giving it a little bit more water. I've still got plenty of space left to put some more water in. And now looking in here, this is looking like the substance has fully dissolved. I want now one extra bit of kit to try and help me. Now the line I've got to fill it up to is just here. You might be able to see that. Paul's trying to zoom in to help you. So what I'm going to do is I'm going to fill it up to start with just the beaker of water. And that's as brave as I dare be. I've got to get to this level here where my finger is. And so to do the last little bit, what I'm going to use is a wash bottle, and I'm going to get my head down so that my line is now lined up with my eye. And now my meniscus is lined up exactly with the line. Put my lid back on, and then if we invert this a couple of times, I've now made a 0.1 molar solution of sodium thiosulfate, which can now be moved from this volumetric flask into a storage jar that I can use to hold my reactants. And that is now ready to go so that I can do all my rates of reaction experiments. So we've looked at trying to sort of do some calculations. You can see why it is so important to balance equations. Without the equations balanced, things don't work. So we balance our equations. We can use moles to try and help us work out what goes on. We can then work out the yield, how much we should get as opposed to how much we did get, and we put how much we did get over how much we should have got, the theoretical amount, and times that by 100. The atom economy is how much atoms we've got worth in something. Sometimes you're even asked to work out perhaps how much nitrogen is in nitrogen dioxide. So you calculate the amount of nitrogen, 14, over oxygen, which is going to be 32, and you can say add them all up, and then you put 14 over the total amount times 100. And then if you need to make up any solutions, concentrations, we make them up using moles. And we've had a go at trying to make up a solution of sodium thiosulfate. So that's a lot of the nasty calculations to try and do. Now, why are we starting to work out all these calculations? Well, we're coming up to probably many students' favourite bit of chemistry, and next week we'll have a look at trying to do some titrations and working out how much stuff reacts with how much of something else. Until then, take care, and I'll see you next time. Thanks for watching. Bye bye.